When NASA designed the final phase of Cassini's mission, a series of 22 daring dives through the narrow gap between Saturn and its rings, engineers were working from a basic assumption that this region of space would be relatively clean and safe to fly through. That assumption turned out to be wrong, and the truth Cassini actually found waiting for it in that gap nearly ended the mission months before its planned, deliberate conclusion. In this video, we're going to walk through exactly what Cassini discovered in the final months of its life, why it caught NASA's own engineers off guard in a genuinely alarming way, and how the spacecraft managed to survive long enough to complete one of the most scientifically productive endings in the history of planetary exploration. If you enjoy real documented space science rather than exaggerated claims, stick around till the end. It's worth being clear from the outset about what kind of terrifying truth we're actually talking about here. This isn't a story about some inexplicable otherworldly phenomenon lurking in Saturn's atmosphere. It's a story about genuine, well-documented engineering risk, the kind that could have ended one of NASA's most celebrated missions in an uncontrolled, scientifically wasteful way, and about just how much of what we know about Saturn's rings and their fate depended on a spacecraft successfully surviving a hazard nobody saw coming until it was already underway. Let's start with the plan itself, because understanding what was supposed to happen makes it much clearer why what actually happened was so unsettling. By 2016, Cassini had been operating at Saturn for over a decade, and its fuel reserves were running critically low. Rather than simply letting the spacecraft drift uncontrolled once it ran dry, potentially risking an eventual unplanned collision with one of Saturn's potentially habitable moons like Enceladus or Titan, NASA's mission team designed what they called the grand finale, a carefully engineered final campaign that would send Cassini through a series of orbits threading the narrow space between Saturn's cloud tops and the inner edge of its rings, before ultimately plunging the spacecraft into the planet's atmosphere to burn up completely. This gap between Saturn and its rings is roughly 1,500 miles wide, and crucially, no spacecraft had ever flown through it before. Every previous mission to Saturn, including Cassini itself during the rest of its 13-year tenure, had kept a respectful distance from this specific region, either staying well outside the rings entirely or approaching Saturn from angles that avoided this particular gap. Based on existing models of Saturn's ring system, mission planners believed this gap would be swept relatively clear of debris, since the gravitational forces at play in this region were thought to prevent significant amounts of ring material from lingering there. The area looked clean and empty in every telescope observation astronomers had ever made of it. That assumption turned out to be significantly wrong, and Cassini found this out almost immediately, once it actually attempted to fly through the region. During its first pass through the gap in April 2017, Cassini's instruments detected far more dust and small particulate matter present in that supposedly clear region than any model had predicted. This wasn't a minor discrepancy easily dismissed as measurement noise. It represented a genuine physical hazard to the spacecraft, one nobody on the mission team had adequately planned for going into the grand finale's first dive. Here's why this mattered so urgently. Cassini was traveling through this region at extraordinarily high velocity, and at those speeds, even microscopic dust particles carry enough kinetic energy on impact to cause serious damage to sensitive spacecraft components. A grain of dust that would be completely harmless, sitting still on a table, becomes a potentially destructive projectile when a multi-ton spacecraft slams into it at tens of thousands of miles per hour. Cassini's instruments, its delicate optics, and its various exposed surfaces were never specifically hardened against this kind of unexpected debris density, because the mission's entire trajectory through this gap had been planned around the assumption that such hardening wouldn't be necessary. This is a matter of basic physics that becomes genuinely alarming once you understand the numbers involved. The kinetic energy of an impact scales with the square of velocity, meaning that doubling a spacecraft's speed doesn't just double the potential damage from a collision, it quadruples it. Cassini was moving through this gap at tens of thousands of miles per hour relative to Saturn, meaning even a dust particle far too small to see with the naked eye could, in principle, strike the spacecraft with enough force to pit or crack exposed surfaces, degrade sensitive optical components, or in a worst-case scenario, damage critical systems needed to keep the spacecraft operational. This is exactly the same underlying physics that requires the International Space Station to occasionally maneuver to avoid tracked debris in low Earth orbit, just applied to a completely different, previously unmeasured environment around Saturn. Faced with this immediate unplanned danger, Cassini's engineering team had to improvise a defensive strategy in a remarkably short window of time. Their solution was to reorient the spacecraft so that its large dish-shaped high-gain antenna, the same antenna Cassini used to communicate with Earth, would face forward during each subsequent ring plane crossing, essentially using it as an improvised shield to absorb any dust impacts before they could reach the spacecraft's more sensitive, more critical instruments and components. This meant that during the riskiest portions of several of the grand finale's dives, Cassini couldn't actually communicate with Earth in real time because its main antenna was pointed away from home, oriented instead to protect the spacecraft's body from incoming debris. This was a genuinely tense, uncertain period for the mission team back on Earth. During each of these particular passes, controllers would send Cassini through the gap, lose direct real-time contact for a period of time while the antenna served its makeshift shielding purpose, and then simply have to wait, without any way of immediately knowing whether the spacecraft had survived the passage intact, until Cassini reoriented itself afterward and re-established contact. Each of these communication blackout periods represented a genuine, unresolved question mark hanging over the entire remainder of the mission. A single sufficiently large piece of debris, encountered at the wrong moment, could have disabled critical systems or even destroyed the spacecraft outright, ending the mission prematurely and denying scientists the wealth of final data that the remaining grand finale orbits were specifically designed to gather. For the engineers and scientists who had spent years, in many cases over a decade, working on this mission, these blackout windows carried a very particular kind of anxiety. Unlike a controlled, gradual system failure that might show early warning signs, a catastrophic dust strike could happen essentially instantaneously, with the very next scheduled communication window either confirming the spacecraft's survival or revealing that contact had been permanently lost. Mission team members have since described these periods as some of the most stressful stretches of the entire 13-year mission, a strange inversion of the more typical anxiety associated with a mission's beginning, like a risky launch or an orbital insertion maneuver, occurring instead near its very end, precisely when the team might otherwise have expected the greatest degree of routine and familiarity with operating the spacecraft. What made this situation particularly unsettling wasn't just the immediate danger itself, but what it implied about how incomplete existing scientific understanding of this region actually was. Scientists had confidently modeled this gap as clear based on the best available theoretical understanding of Saturn's ring dynamics and gravitational interactions. The fact that reality diverged this significantly from those models, in a region considered important enough to root an entire historic mission finale through, was a sobering reminder of just how much remained genuinely unknown about the detailed structure of space immediately surrounding Saturn, even after over a decade of dedicated study by an orbiting spacecraft. As the grand finale's 22 orbits continued through the following months, Cassini's team refined their understanding of the dust hazard with each successive pass, adjusting their defensive procedures based on data gathered during each previous crossing. Fortunately, while the dust density in the gap was higher than expected, it wasn't uniformly hazardous across every single crossing. And Cassini's shielding strategy proved effective enough to get the spacecraft through all 22 planned orbits without catastrophic damage. But the tension never fully disappeared because each crossing still carried genuine, non-trivial risk, right up until the mission's final deliberate plunge into Saturn's atmosphere in September 2017. This unexpected dust density also turned out to be scientifically valuable once the immediate danger had been successfully managed. Cassini's Cosmic Dust Analyzer, an instrument specifically designed to directly sample and characterize small particles it encountered, was able to gather genuine, unprecedented data about the composition and density of material, occupying this previously unexplored gap. This gave scientists their first direct, in situ measurements of exactly what kind of material exists in this specific region of space, information that simply couldn't have been gathered any other way. Since no telescope, no matter how powerful, can directly sample the physical composition of dust particles from millions of miles away the way a spacecraft flying directly through that material can. This turns what began as a genuine engineering crisis into a valuable illustration of how spacecraft engineering and scientific discovery are often deeply intertwined in ways that aren't always obvious in advance. The same dust that threatened Cassini's survival also became one of the final mission's genuinely novel scientific findings, precisely because the spacecraft happened to be carrying an instrument capable of turning an unwanted hazard into a measurable, characterizable phenomenon. Few missions managed to extract this kind of dual value, both surviving a previously unknown risk and simultaneously using that same risk as an opportunity for direct scientific measurement from a single unplanned discovery made this late in a mission's operational life. The data revealed that the particles Cassini encountered in the gap were generally quite small, consistent with fine dust, rather than larger, more dangerous debris, which helps explain why the spacecraft's improvised antenna shielding strategy proved sufficient to get it through safely. But the sheer quantity of this fine material present in a region previously assumed to be relatively clean forced scientists to reconsider their models of how material actually migrates and distributes itself in the space immediately surrounding Saturn's ring system. This connects directly to the broader ring rain phenomenon that Cassini documented throughout its final orbits. The process by which material from Saturn's rings continuously falls inward toward the planet, gradually eroding the ring system over time. The unexpectedly dusty gap between Saturn and its rings turned out to be part of this same ongoing process, one small piece of evidence within a much larger picture of how actively material moves and gets redistributed throughout Saturn's ring environment. It's worth pausing here to really appreciate the layers of risk NASA's engineers had to manage simultaneously during this entire campaign. They were already flying an aging, fuel-depleted spacecraft through completely uncharted territory, on a trajectory specifically designed to end in the spacecraft's own destruction, regardless of what happened during the grand finale itself. Adding an unplanned, unexpectedly severe dust hazard into that equation meant the mission's final months carried a genuine possibility of an early, unplanned, and scientifically premature end, one that would have cut short the very observations the entire grand finale campaign had been designed to gather in the first place. This raises a question worth sitting with. What would have actually happened if Cassini had been more seriously damaged or destroyed outright during one of these early ring gap crossings? Well before its planned final plunge in September 2017. The mission would have ended in an uncontrolled, unplanned manner, and NASA would have lost the opportunity to gather the detailed atmospheric composition data, the ring seismology measurements that later helped resolve Saturn's long, mysterious rotation rate, and the direct measurements of ring rain that ultimately reshaped scientific understanding of how quickly Saturn's rings are actually disappearing. In other words, one of the most scientifically productive periods of the entire 13-year mission came remarkably close to never happening at all, cut short by a hazard nobody had adequately anticipated going in. It's worth remembering just how much downstream scientific work depended on Cassini successfully completing this entire sequence of orbits. The ring seismology analysis that finally determined Saturn's precise rotation rate, published years after the mission ended, relied on ring observation data gathered specifically during these final, riskiest orbits. The detailed measurements of ring rain that reshaped understanding of the ring's age and eventual fate similarly depended on data gathered during this exact same window. Had Cassini been lost partway through the grand finale sequence, both of these major scientific results that continue to shape how planetary scientists understand Saturn years later, might never have existed at all, or would have needed to wait for an entirely new and likely decades-distant follow-up mission to attempt gathering comparable data. This close call also offers a valuable, sobering lesson about the limits of even the most sophisticated scientific modeling. Saturn's ring system had been studied for centuries through telescopes and intensively for over a decade by Cassini itself, before the grand finale even began. Despite all of that accumulated observational history, a region as significant as the gap between the rings and the planet itself still held a genuine, potentially mission-ending surprise that nobody had fully anticipated. It's a reminder that even our best current models of well-studied objects in our own solar system can still contain significant, consequential gaps, and that actually sending a spacecraft directly into a region, rather than relying purely on remote observation and theoretical modeling, remains one of the only reliable ways to truly verify what conditions are actually like there. There's an interesting parallel here to how mission planners approach risk more broadly across deep space exploration. Every mission that ventures into genuinely unexplored territory, whether that's Cassini threading the ring gap, the Parker Solar Probe repeatedly diving closer to the Sun than any spacecraft before it, or future missions planned to fly through the plumes of Enceladus or land on the surface of Europa I, inherently carries this same fundamental tension. The most scientifically valuable data often comes from exactly the regions where existing models are least reliable, precisely because those are the places nobody has ever actually measured directly before. Cassini's dusty ring gap surprise is a clear, well-documented example of this broader pattern playing out in real time, with real consequences, during one of the most closely watched mission conclusions in NASA's history. The Parker Solar Probe comparison is particularly instructive here. Before that mission launched, scientists had reasonably good theoretical models of the Sun's outer corona, the region Parker was specifically designed to fly through repeatedly, but there remained genuine uncertainty about exactly what conditions the spacecraft would encounter that close to the Sun's surface. Engineers built in substantial safety margins and protective heat shielding specifically because they anticipated this kind of gap between theoretical prediction and physical reality. Cassini's grand finale, by contrast, had comparatively less built-in margin for this specific kind of unexpected hazard, precisely because the ring gap had been assessed as a genuinely low-risk region before the mission began, making the discovery of unexpectedly high dust density that much more consequential when it actually happened. It's also worth noting how this particular hazard connects back to the ring rain findings we've discussed as part of Cassini's broader final legacy. If material is continuously migrating from Saturn's rings inward toward the planet, gradually eroding the ring system over time, then it stands to reason that the space immediately between the rings and the planet's atmosphere would be more actively populated with migrating debris than a simple static model of the rings might suggest. In hindsight, the unexpectedly dusty gap Cassini encountered wasn't really a separate, isolated surprise. It was direct physical evidence of the same active, ongoing ring erosion process that Cassini's other instruments were simultaneously documenting through completely different measurement techniques. The danger the spacecraft faced and the scientific discovery about the ring's true age and fate turned out to be two sides of the very same underlying phenomenon. This connection is worth emphasizing because it illustrates something important about how scientific discoveries often unfold in practice. They rarely arrive as neatly isolated, standalone facts. Instead, they tend to emerge as different pieces of a single, larger, interconnected picture gradually assembled from multiple independent lines of evidence gathered by different instruments, often under very different circumstances. The dust hazard that nearly threatened Cassini's survival, and the separate discovery that Saturn's rings are eroding and raining material into the planet faster than expected, weren't two unrelated findings that happened to occur during the same mission. They were two different observational windows onto the exact same underlying physical process, each reinforcing and helping to explain the other. Let's talk about how the mission team actually managed this evolving risk across all 22 orbits, because it's a genuinely impressive example of adaptive engineering under pressure. Rather than treating the antenna shielding strategy as a fixed, one-time solution, Cassini's engineers continuously refined their approach based on data gathered during each successive ring plane crossing. Early passes were treated with particular caution, given the complete lack of prior direct measurement of conditions in this specific region. As more data came in confirming that the dust particles encountered were generally small and that the shielding strategy was working effectively, the team gained increasing confidence in the safety of subsequent passes, though the fundamental risk never completely disappeared given the inherent uncertainty of flying through a region this poorly characterized. This iterative approach to risk management meant the mission team was essentially learning and adapting in real time, refining their understanding of a genuinely novel environment, one orbit at a time, with each successful pass providing slightly more confidence, though never complete certainty, about what to expect during the next. This is a fundamentally different mode of operation compared to how most of Cassini's 13-year mission had proceeded, where most maneuvers and observations followed carefully pre-planned sequences validated well in advance. The grand finale's ring gap crossings represented one of the few extended periods in the entire mission where the team was genuinely improvising a safety strategy in response to real-time discoveries, rather than executing a fully pre-validated plan. This kind of real-time adaptive risk management, adjusting procedures mid-mission based on freshly gathered data rather than relying solely on pre-mission planning, has become an increasingly important part of how NASA approaches the final, riskiest phases of long-duration missions. Cassini's grand finale is now frequently cited within the planetary science community as a case study in exactly this kind of adaptive engineering, demonstrating how a mission team can successfully respond to a genuinely unexpected, potentially mission-ending hazard discovered only after the spacecraft was already committed to its final, irreversible trajectory. Let's address a few common questions people tend to have about this part of Cassini's story. Did Cassini actually take any physical damage from these dust encounters? Based on available telemetry and the spacecraft's continued successful operation through all 22 grand finale orbits and its final planned plunge, there's no strong evidence that Cassini suffered significant damage from the dust it encountered in the ring gap. The antenna shielding strategy appears to have been genuinely effective at protecting the spacecraft's more vulnerable components throughout this risky final phase. Could this same kind of unexpectedly dusty gap exist around other ringed planets like Uranus or Neptune? It's certainly possible, though no spacecraft has ever attempted a similarly close direct fly-through of the regions immediately surrounding those planets' much fainter ring systems. So there's currently no direct observational data to confirm or rule this out. Given that Cassini's experience at Saturn demonstrated just how unreliable remote telescope-based models could be for this kind of prediction, any future mission attempting a similar maneuver at one NASA just confirmed Voyager 1 found something. Uranus or Neptune would likely need to plan for comparable uncertainty and build in similar contingency measures. Why didn't NASA test this region more cautiously before committing Cassini to the full 22-orbit campaign? To some degree, they did approach the first crossing with appropriate caution, treating it as a genuine unknown given the complete absence of prior direct measurement. But the entire grand finale campaign was designed around Cassini's rapidly depleting fuel supply, meaning there wasn't the luxury of extensive, incremental testing before committing to the full sequence of dives. The mission team had to balance the value of gathering data as quickly and thoroughly as possible against the risks of an approach that hadn't been previously validated, ultimately deciding that the scientific value of proceeding outweighed the uncertainty involved, a calculated risk that, in this case, paid off. Was this dust hazard ever presented to the public at the time, or was it kept quiet until after the mission ended? NASA was reasonably transparent about the challenge during the mission itself, with mission updates and press briefings during the grand finale period acknowledging the unexpectedly dusty conditions and the antenna shielding strategy being used to manage the risk. It wasn't a secret uncovered only in hindsight, though the full scientific significance of the finding, its connection to the broader ring-rain phenomenon and Saturn's evolving ring system, became clearer through more detailed analysis published in the years following the mission's conclusion. How did the mission team's mood shift once they realized the shielding strategy was working? Accounts from mission scientists and engineers describe a gradual, cautious relief as successive orbits confirmed the spacecraft remained healthy, though genuine tension persisted throughout the entire 22-orbit sequence, given the fundamentally unpredictable nature of the hazard. Unlike a problem that could be definitively solved and closed out, the dust risk remained an ongoing, orbit-by-orbit uncertainty right up until Cassini's final deliberate atmospheric entry in September 2017, meaning the mission team never really got to fully relax about this particular danger until the mission had concluded entirely on its own intended terms. So, to bring this all together, what was the terrifying truth Cassini's final moments actually revealed about Saturn? It wasn't some inexplicable, unsettling mystery in the traditional sense. It was the very real, very concrete discovery that a region of space considered safe enough to route an entire mission's historic finale through was, in fact, considerably more hazardous than any existing model had predicted, a discovery that put the entire remaining scientific campaign at genuine risk of an early unplanned end. That gap between Saturn and its rings, once assumed to be a clean, empty highway, turned out to be an active, dust-filled extension of the same slow-motion process gradually eroding Saturn's entire ring system, one that very nearly derailed one of the most scientifically important final campaigns in the history of planetary exploration before it could be completed. Cassini survived that danger, and in doing so, delivered some of the most valuable scientific data of its entire 13-year mission. But it's worth remembering just how close that outcome actually came to going the other way, and how much of what we now understand about Saturn's rings, its rotation rate and its ongoing evolution, depended entirely on an aging spacecraft successfully surviving a hazard nobody had fully anticipated, using nothing more than its own communications antenna, repurposed on short notice, as an improvised shield against a threat that existing science simply hadn't seen coming. There's a broader takeaway here worth carrying forward into how we think about future missions attempting similarly bold, previously untested maneuvers. Every time a spacecraft is sent somewhere genuinely new, whether that's threading a narrow gap around Saturn, diving closer to the Sun than any prior mission, or eventually attempting to land on the surface of an icy moon like Europa. There's an inherent gap between what our models predict and what turns out to actually be true once we get there. Cassini's dusty, dangerous final months are a vivid, well-documented reminder of exactly why that gap matters and why some of the most valuable scientific discoveries continue to come not from safely observing from a distance, but from the calculated risk of actually going and finding out firsthand. If you found this breakdown interesting, make sure to like this video, subscribe to the channel, and let us know in the comments. Did you know Cassini's final orbits were genuinely more dangerous than NASA originally expected, and that its own antenna had to double as a makeshift shield to survive them? See you in the next video with another real grounded space story worth exploring.